which looks very plausible, but anyway, it's not proved so far. It's this nonlinear Schrödinger equation. In supercritical case, d equals 3, is three-dimensional. It's a realistic situation describing many physical problems. And it has constant of motions. I1 is just integral psi square dr. This I2 is just integral psi square minus 1/2 psi 4 dr is a Hamiltonian. And it's if I2 is negative, the initial solution blow up, goes to blow up. This is an absolutely strict result. It's a strict theorem. And the question is how to find the behavior near in the vicinity of the blow up. This is a very simple conjecture. That this solution has a special solution of the following form. Now this special solution is size 1 t naught minus t 1/2 plus I mu some function f on r divided by t naught minus t in 1/2. Suppose this is a function. One can consider that it's a symmetric case. And this mu is a known constant, but this equation is compatible. This solution is compatible with the equation, but it's not compatible with the constant of motion. If you look for constant of motion, you see that what at is behave like t naught minus t I1, and I2 it behave like 1/2 t naught minus t in 1/2 I2. So there are only two possibilities, because this is certainly positive. So I1 is equal infinity. And about I2, there are two possibilities. I2 equal infinity or I2 equal 0.
Is that the same I1, I2 on both sides?
Yes, the same. It is just, but if you look, the same. So for these special solutions, and actually this, from a physical viewpoint, this condition is preferable because it means that there is no flux of energy from the infinity. And it makes possible to find mu numerically, which mu becomes 0.5, something like this. I don't remember with better accuracy. But what's interesting, of course, this solution is a formation of singularity, which is not integrable because I1 is infinite. So psi square behaves like some constant c divided by I r square. R tends to infinity. Can somebody prove that the same singularity exists for a real solution which has a finite value of I1? Still open question. I must add that it was approximately 10 years ago. It was a lot of energy was invested into numerical solution of this equation, including specially aimed to targeting to look for this behavior. There were two groups compete, one in Moscow, another in Courant, and it was finally, if you the exceeding of initial data, psi in maximum by psi square by psi 0 square, was finally 10 to 25. There are some special self-tuning scheme where used with adjusting scheme following for this singularity, and they demonstrated this behavior with enormous accuracy. So it's almost clear that this result is correct and this behavior is a generic behavior. But there is no strict mathematical proof, and this is, I think, this is a very important problem because it's very simple and fundamental. Of course, that this is only example. One can write if the method would be found, it would make possible to solve a lot of sister problems to this.
So I thought the way we might conduct this is to give each of our three speakers an additional 10 minutes, but a maximum of 10 minutes, to elaborate their remarks or answer any questions or make any comments. So why don't we start with you?
Well, as is usual when giving a lecture, so immediately afterwards I thought of a few things I wished I had said. It's rather nice to have the chance to do it. It's never happened to me before. But I will try and be extremely quick about it. It's just to remind me what they were. The first one was just to draw a quick analogy between Feynman's theorem and Turan's theorem. If you remember, with Feynman's theorem, I said if you've got the constant which is close to 2, then you can show that your set is close to an arithmetic progression, and as you gradually relax, the structure sort of becomes more interesting, the dimension of the arithmetic progression goes up, and so on. A similar but simpler phenomenon occurs in graph theory with Turan's theorem. Now that says that if you the largest number of edges that a graph can have without containing, let's do it for a triangle, but it generalizes to K4 and so on, occurs when you take 3 parts that are as equal as possible. Sorry, let's make that, this is the largest without containing a K4, I beg your pardon, so a triangle would be bipartite, so it's a bit more interesting. I want to avoid containing 4 vertices that are all joined to each other and put as many edges as possible. The best way of doing it is to have 3 vertices, 3 blobs of nearly equal size, and join them completely. And then it's obvious by the pigeonhole principle that you can't have a K4. Now, what if you had nearly as many edges as are allowed by this example? Then it turns out there's a result of Erdős, somebody can help me, there's Erdős and Erdős, Stone, anyway. All right, so which implies that the graph approximates this graph. So just as with Feynman's theorem, you still have approximately an arithmetic progression to start with. Here you still have it in the sense that you can just change a few edges and you get back to this graph. Now what happens if you gradually relax it further? Well, you can say a few things, but it's definitely not completely understood. So if you say you don't have any K17 and you have at least n squared over 10 to the 10 edges, there's not a huge amount you can say, I think, that goes really beyond what you can get from using Semirade's uniformity lemma, or regularity lemma. And you can deduce some things about that graph directly from that, but there's sort of somehow not as much as you'd like to say. So that's just somehow a similar type of situation. Second very quick remark was that a related reason to the ones I was saying about why those problems are hard is that very often there are somehow 2 ways of going about constructing an extremal example that do opposite things. And even if one of them is obviously better than the other, still somehow it seems to be difficult to prove something and take account of both of those examples at once. So one example with Ramsey's theorem, if you want to avoid a large complete graph, a very natural way to try to do it is to choose n squared pieces, have no edges inside, and have all the edges in between, etc. Now that, you can see, doesn't contain a complete graph of size more than root n, because if you want, or an independent set, because if you want a complete graph, you've got to have at least 2 things in the same blob, and that rules it out. And if you want an independent set, you could have 2 things in different blobs, and that rules it out. So one technique for avoiding complete graphs is the pigeonhole principle. And in fact, Turan originally thought this probably was the best example. He conjectured that RKK was of order k squared. This was before Erder showed that the random methods gave much better. But even so, when you're trying to think about the problem, sort of related things like this keep coming up. You sort of, well, you may not have precisely this example, but you might have other things that use pigeonhole principle type things, and it's very difficult to take account of them all. And the third remark, and perhaps I could say that, just emphasize the same thing happens with Roth's theorem. I mentioned that Behrend had a thing that does better than random, and again, it's hard to sort of take account of it in a proof. And the third thing I just wanted to say very quickly is that I mentioned it on the last slide, but didn't, or put it on the last slide, but didn't emphasize it, but it is important. There is no really satisfactory analog of Semirades' regularity lemma when the number of edges in the graph is not proportional to n squared. So if you want the number of edges to be n to the, or the density of the graph to be n to the minus a third or something, very little is known.
Even if density is logarithmic, it's small?
Well, the smaller it is, somehow the worse the situation becomes.
No, n over logarithm.
Oh, see, n over no, I think even that is not very much is known. And that's actually is regarded by many people as a very central problem. Now, there have been attempts to deal with it, which have been successful for some problems, but I think it's a fair thing to say that probably more could be done.
But the fact we have this bad example doesn't it indicate that it will go down?
Yeah, it indicates you'd have to change the statement somehow. So you have to come some sort of idea of classifying it in some cleverer way than just blobs. But it's not obvious how to do that. I don't have any particular suggestions.
Just wanted to add about Semirades' lemma that it fits a little bit in the philosophy that Rafi Kochman was explaining, because after all what it says is that you have this huge graph. It's very complicated to think about what's connected to what, but you can effectively think about it as a much smaller graph with the vertices blown up and then just random connections between them. And you don't really have to know anything more about those connections that they look random.
Shall I hand over?
So Cyriakin Krishnamurti asked the first part the word which did not appear in the discussion is new concept.
New.
When you discuss algorithmization of mathematics.
Yeah, okay, so I was oversimplifying. I didn't mention anything like making good definitions or generating problems. I just sort of oversimplified by saying it's trying to prove theorems. And of course, there is more to it. But I would have similar remarks. I mean, if you try to think about how people come up with new definitions, again, I certainly don't think it's going to be sort of trivial to automate or anything like that. But nevertheless, usually you come up with some explanation about how you don't sort of, people don't magically say, look, here's a well, they sometimes do say it, but this is dishonest. They don't say, here's a definition which magically does all sorts of wonderful things.
Which you could say something. This example which I see is the center one of the central examples in sort of 20th century mathematics is the notion of categories. So I'll be very interested to see how you think about it. What? Listen, Bellison talking more.
But even that you can
You
explain
need to
to some
have this in mind, even if you don't need this. This is two different things.
No, of course, physics is the apparent physics literature now all the time. And I have my, so to say, if you read the paper of Moore and Seiberg, we're not interested at all in inventing categories. So you read it and you have very interesting remarks. You have A is equal to, you have two things, which in describe like sets, the A and B, and they prove that A is equal to B once. Then they prove that A is equal to B twice. And then they prove that the first way they prove that A is equal to B is the same as second way they prove A equal to B. You first think they're crazy, and then you realize they have vector space, actually more complicated object. You construct one isomorphism, then another isomorphism, and they prove that two isomorphisms coincide. So this is a way of thinking. And the tensor categories appear naturally in their paper. They just write in appendix that the language was clarified by Deligne, but the concepts appear. And so I definitely know a number of examples where people have to use categories to prove results when the category is not a part of a question. So one more, I would be interested to see how you think that algorithmization could invent categories.
Category is a directed graph.
No.
Well, I think the way to answer that sort of question is just to look at how human beings did it, but try and, again, if some people I think believe that human brains are somehow very, very special objects that do magic. But if you don't, and you just look, people have various, again, these mathematical reflexes. I'm not saying this is a complete answer to the problem, of course. But they would say, I've got these things, can I generalize, can I generalize, can I generalize? That's one sort of mathematical reflex. So, has this situation got anything in common with this situation? And actually that is, okay, so what you're asking, I think it probably is one of the hardest things for computers to do, because generalization, again, involves spotting patterns.
But in fact, opposite, the category language is the most computerized.
That's a different
Well,
thing.
there is an obvious question. There are different kind of conceptions. Some are right about categorization of the brain. Category exactly is out of categorization, which is kind of a parallel processing. And just categorization appears for lower animal, for fish. Yeah? So fish in the way of categories. So
I've got
you
very
observe
strong
many objects and then you
ally
make
here, I
concept.
It's much broader than mathematics.
Just to be
It's a much broader...
Come.
Yeah, it's not mathematical concept. Yeah, it's much broader.
No, I have an example.
But come down.
Take.
Yeah. Okay, just an example in the totally different direction from your example. I think that I would wonder, I was wondering myself how to explain in the sense that Tim was trying, how do we explain how we came up with the proof or with the definition? The example that of the problem that if you have an n by n square and you remove the antipodal squares, the two squares in opposites of the diagonal, you cannot partition it to dominoes. Of course, it's not interesting if n is odd, but if n is even, it's an interesting question. And I think that, well, I'm sure all of you know the solution, but the solution involves the creation of something that was not there to begin with, which is the coloring, or chessboard coloring. How did we, when you see this proof, someone tells you, if you didn't think it up yourself, and you ask him to explain how he came up with it, I don't think there is a good one, or if there is, I'd like to hear it. Or if you come up with it yourself, I don't know if you can explain. So that's...
No, but
I can't do it on the spot, but I think a plausible story about how one came up with a proof could be constructed for that example.
This is perhaps not an example so strong as, because in your head you have image of... in your head you have image of square, only one square. In computer, you put all kind of square images, in particular chess blackboard, and then it's come immediately. So point is that we keep very few images. When problem given about something, computer may immediately go through all images of this something. And then it's chessboard inside, and solution is immediate.
But you mean this could not have been solved by a person that has never seen a chessboard? A mathematician that has never seen a chessboard?
Very good, but we talk about how computer invents
No,
this.
we. I mean,
How we, I
also.
don't know.
Well, that's what we want to automate.
More easy.
But really, again, nothing special about that. How you generate sentences, how you speak. You don't think before you talk, right? You make a sentence before you think about that. How you do that? Nobody knows that, yeah? Why to ask so sophisticated questions about mathematics?
I think that's a harder
No,
problem.
how
It's
do you
again
say?
wrong, because language is so high level of abstractization that
No, I'm not saying abstractization. How,
mathematics did not come to
no,
this level.
without abstraction, how you generate sentences?
Huh?
How you generate sentences with such
But it is
complicated
much
grammar?
more
No.
complicated than any mathematical theorem.
Yeah. I think this is all very interesting. So, I think we will, something else. I think we'll go on to our.
But Elias, I think Laszlo wanted to say something, not? So come. Yeah, you get what is. Look, chairman want to finish. I want to keep you till reception starts. So we have different.
A little bit provocative here, and because we had this discussion about good problems, bad problems, natural problems, and so on. So let me bring up the fact that there is a computer program which generates problems, and well, I think it generated no. It's not predictable problem, and it had at least one, actually several good problems.
Can you say one computer generated?
Yes. If chi denotes the chromatic number of the graph, and R denotes the rank of the adjacency matrix, the computer program generated this question. And that question turned out to be equivalent or closely related. Okay, so is the rank of the adjacency matrix, and actually, as it turns out, this is false, and I think it's Noga and Seymour who first disproved it, and then there are now Avi. I think Avi has the paper which has. With Noam Nissan, which produces the largest gap.
How question appear if it happened to be wrong with this computer? The computer did not find counterexample.
Yeah, but let me add that the conjecture is closely related.
50 examples.
Well, I know a little about the program. I can tell it to you. I don't want. I mean, it's stolen time. So let me just add that this problem turned out to be very, it's still open whether something like this to the log R bound like this is valid, and that's can be translated to a very basic problem in the theory of communication complexity. I can describe to you the system. It's done. It's in Houston. Semyon Feitlovich is the name of the person who is responsible for it. The program has a list of interesting graphs and a list of parameters, and tries to find relations between those parameters which are valid for all interesting. It's just built in. Right.
This is a very nice problem. I think what is known is that it's not power-like.
Yeah, right. And to be entirely fair, let me add that it turned out that this problem was also discovered by a human. But it was an independent discovery and somehow interesting.
Wrong. This only that. It's main problem that computer.
There are other papers, by the way, written on the problems raised by this program. So it's
there are only a finite number of parameters, right?
Yeah.
So it's not so unexpected that
No, but there is a
look at most possible combinations.
And these problems which turned out to be true.
But you have a finite number of parameters that the computer will check that place where you will check for each possible question. I mean, you can define the simple more possible question, and then the computer will just go ahead and check. I mean, I don't see it as mysterious.
The only mysterious is
All right. Okay, so the next one.
actually to come back on that estimate debate. The only known exit bound is the previous bound.
There's no point of holding this in your hand when you don't turn it on.
No, but
Okay. What I remember from the problem is that the only known estimate is the obvious estimate, which is an exponential estimate in R or something like that. Is this correct? And
Yeah, that's trivial.
then there was some improvement. I think someone in Yale who computed even the coefficient. And this is related to problems in Banach spaces, but in any case. So I want to try to elaborate something I haven't really done in public, so it's maybe a good challenge for you to catch me if I'm telling you something which is a lie. Essentially, it's the affirmation that in certain cases you can prove that these global solutions in dispersive PDEs actually do exist by some numerical, well, whatever the partial knowledge one has, and certain numerical experiments. So I quickly tried during Vitaly's talk, I hope he will forgive me for that, to work out the numerics of the example. What I would consider is, say, a 3D supercritical. No, supercritical here is not in the sense of Vladimir Zakharov, but it is supercritical with respect to the H1 norm. Defocusing, so we do expect, or at least we may hope, that there is no singularity formation for classical data. So let's specify the equation. Let's say this guy. So basically we do not know very much about that equation. What we do know are two things. The first thing is that there are local solutions. Provided in that case, provided you have local solutions in time, provided we take a data, say U0 in HS on R3 with S should be at least equal to 7/6. I mean, these numbers are not random, they are the exact numbers, okay? So 7/6 is unfortunately bigger than 1, and so we cannot use the conservation of the Hamiltonian to extend these local solutions to global solutions. Nevertheless, we know that somehow these local solutions will be global as a consequence of the method, provided they are small. Now, one can be more precise about small. And in fact, it is enough that the free solution of the equation should be small in certain norms. So if I call this phi, what I know, for instance, is that if the free solution is small in a norm, which here is the norm L15, so I take R3 times 0 infinity, then that local solution will actually be a global solution. Now notice that the animal which is here is something one can calculate explicitly in terms of an oscillatory integral. So if I give you a concrete smooth function phi, well, you can see what happens using standard facts about oscillatory integrals and maybe a little bit numerics conceivably for small time, what is going to happen with this expression, which is simply a standard oscillatory integral. Now, the logical statement I made was the following. Assume that we start with the classical data. I mean, take it radial, for instance, but it doesn't really matter, which is not small. Assume that there is a global U which scatters. I won't explain you that in detail. Then it is possible to prove this by computer. And from the argument you will see that in fact one can also do that for bounded regions in spaces of classical data just by taking nets and eventually having estimates which are much better, say, than the spacing of the points in the net with what is known, and in fact to conclude that you will have this phenomenon, provided it is true, of course. And people may believe that, and it could very well be the case, that it's possible to have a classical data here which somewhere will start developing singularities. But I mean, if you assume that this is not going to happen, then, well, it's possible to prove this global existence and scattering just by numerics for any bounded set in any whatever smooth phase space. So let me quickly. Well, here I will show it for one solution, but you can always take a family of, say, if I consider some bounded region in phase space, some ball in phase. So what I will do is take a net, and if my estimates are sufficiently good, then I can do it by perturbation. I mean, this will be a byproduct of the argument. But already for one solution, it's not uninteresting because there isn't a single one known. There is not, I mean, basically, here we are on the line, yeah? In R3, there is not a single large solution, no. So we can as well try to construct one. So let me just show you.
The second line, what do you mean by that? It's almost...
This line?
No, on the left board.
On the left board. Where?
What do you mean by the line? Global solution which scatters.
Yeah, I didn't explain you. I won't do that. No, I only have 10 minutes, so I have to leave a little bit. Let's say that it essentially behaves like you want it, and some people expect it to behave.
But is that something you can check numerically, or is that an assumption?
Well, okay, you can do numerics, and then either these numerics are conclusive or they are not conclusive. But if this thing happens like you expect it to happen, then the numerics at some point will be conclusive.
Okay. So if the numerics are good,
you will prove it. Of course, if this thing does not happen, you will not prove it. I mean, this is clear.
But that statement is really a numerical statement, the number 2.
So assume that your solution behaves good, then you will prove it by numerics. Conversely, if your numerics, I will tell you some scheme. If your numerics are conclusive, then you will prove it. I cannot say that you will prove, assume that U0 phi is a classical thing, then you will prove numerically that U is global and scatters, because it may be wrong. But if the procedure works, it will be correct, and you have a procedure. So you have a procedure which will work if and only if it is true. So let me describe to you the procedure. So of course we start with a large time. You have a data, you can do numerics. Now, what you get from numerics? From numerics, you will get a bunch of numbers. So what can you do with a bunch of numbers? Well, the obvious thing to do with your numbers, which are supposedly going to tell you what that solution should look like between 0 and t, say on a bounded spatial region, you start, say, from t equals 0, you have this phi, which is here, and then you try to see what happens later on, and you just try to use whatever kind of numerical scheme to approximate, to construct a solution. So you have numbers. What you do with these numbers? Well, you interpolate these numbers. Any kind of reasonable procedure, I don't know, use wavelets or something like that, which is efficient to do this interpolation. So what I do here is construct a function, let's call it, say, u1 of xt, for, say, t is less than capital T, this would be capital T here, by interpolating whatever the numerical data you have. So, if you expect that the things remain smooth, of course, what you expect is that somehow this u1 should at least satisfy approximatively the equation. So this is the third step. We have this u1 here, which is a very concrete function, which is certainly smooth. No, the amount of smoothness, I mean, that will depend on the numerical data. But in any case, what you can do, there is no problem there, is throw u1 back in the equation. So what do we get? So what we're going to have is let's call it u twiddle. So I u twiddle t plus Laplacian u twiddle minus u twiddle at the power 6 equal to a certain error, let's call it epsilon of x and t. And that is considered for t less than capital T, where this epsilon xt is a certain explicit function. So if you assume that the thing works nice, what we expect is that this error which you will have here is small. And small in appropriate norms. I mean, if you start from very smooth, then and you do the numerics far enough, well, then you expect that you could make this epsilon as small as you want, provided, of course, you keep the time t fixed here. Okay? Well, the third thing is that you're right. So we still restrict little t to that time capital T, and you write u twiddle as, say, you try to write the real solution u as the sum of u twiddle plus v, where v will be an error. So v satisfies the difference equation, which is simply ivt plus Laplacian v minus v at the power 6 plus some stuff here, which will depend on u twiddle and on v, will be of a lower degree, and will involve terms which do have a dependence on v, because these guys are going out, equals, say, plus epsilon xt equals 0, to be solved with initial data, of course, v0 equals 0, for instance, for time t less than t. So here, I mean, this is not completely obvious, but basically the analysis which one can perform for the given equation, that kind of analysis can also be performed for the difference equation. One of the reasons, say, is simply that the leading nonlinearities, they are the same as in the given equation, and in fact these methods are sufficiently robust to be able to treat that difference equation as well. Now here we have an inhomogeneous equation, so what happens is that if you want to go up to time t, you go by sufficiently small time intervals basically on each time interval you can get your solution V by some kind of Picard scheme. The fact that that Picard scheme converges is a non-trivial fact, and you need to work in a space here HS with S sufficiently large, and is essentially the same proof as a proof of the local existence. Now, what happens is that if epsilon is sufficiently small in the right norm, then you will be able to go all the way up to T. Now, how small will epsilon have to be? Well, the most crude estimate would be something like an epsilon in what HS for S sufficiently small should be smaller than, say, some exponential minus T or something like that. But you don't care because T is fixed, and your epsilon, you will get as good, as small as you want, provided you do your numerics enough. Of course, except in the case that there is a singularity formation. So either you can get, by numerics, this thing happening, which will, of course, be the case if U remains smooth, or, of course, I mean, it's going to be that you have a singularity. Now, if you assume there is, so basically that thing will give you, by numerics, sufficient arbitrary small epsilon, assuming if and only if there is no singularity formation for that particular solution. So if we accept that it's going to happen like that, then we can make this epsilon sufficiently small. So at that stage, what you do control is the U up to time T. So, and at that stage, I mean, this is something you can do basically for any equation, but the place where you use the fact that there is dispersion is the following. At time T, what we have, this is the end, at time T, we get U twiddle T, which is a new function phi 1, and which is basically, if that thing works, the same as the function you have gotten from your numerics, ut. So you get ut, which is u at time t, which is, if that thing is then, and gives you sufficiently small epsilon, essentially the same as u twiddle t, which is the guy which you get from your interpolation. Now, how do you conclude? Well, basically, to go beyond t, what you need to know is that that is small. And I could have called, let's just call it, okay, let's call it phi 1. What you need to know at time t is that that guy is small. So this is something I said can be checked numerically, and is something which is going to happen if you assume that you have scattering. So the fact that you have scattering is equivalent to the fact that if t, I mean, this is, if you want, what is behind it, the fact that you have scattering is equivalent to the fact that if you take that solution of the original problem, ut, then for sufficiently large t's, if you apply the free evolution on ut, then what is here will be controlled in L15 and will be small in L15. This is a consequence of the scattering. And to verify this at that point, this is something you can just do by calculating this oscillatory integral for a concrete function. So everybody, I mean, the only little thing is that you have to control it on an unbounded domain in space-time. But essentially, because of the smoothness, you know what are the decay properties anyway, so you only have to come to control it in a finite box, right? So, I mean, you have to calculate that integral. My feeling is that this scheme would even work much better if the thing was dissipative instead of just dispersive, but I don't have enough understanding of dissipative equations. So say for Navier-Stokes, you have something which is much stronger than dispersion. It's just going to disappear completely. So.
But there are numerical experiments.
Just.
Take this one. So, what I want to say is that in the case of supercritical equations, like supercritical wave equations, there are a lot of experiments. I don't quite trust them, of course, but there are lots of experiments that show that there is no breakdown, and I think it's kind of similar to what you are doing.
So what I'm doing is that it's not completely dumb theoretically, because if you would really push it enough, it would not only be, it would be possible really to prove the theorem like that.
Well, you'll prove that there are you'll show that there are solutions that exist globally, which I think it's almost obvious. There must be, of course.
Except that we don't have one.
Well, it depends. I mean, of course, we have a lot of them with small data. So now you have to quantize what you mean
big
by
solutions. Just take a big bump.
Right. Okay.
So, what I was saying is that if you can, you see, this thing is quite quantitative. So if you have a bounded region in a classical smooth phase space, you can have a sufficiently fine net, and then there you would have these estimates, whatever with etc., and then you go by approximation.
You never can prove it for all.
No.
It's a smooth function with compact support.
Well, you will prove it in any bounded region of phase space. Well, that's already not so bad.
No, of course. The theorem that always exists for any good classical solution.
So I think in this particular case, the problem is, as far as I can tell, is that there are probably solutions which break down, but they're unstable. The same.
Well, that's your belief.
That's my belief.
Okay, so there's
numerical experiments cannot detect that, unfortunately. But yeah, so I understand. So you want to sort of be sure that there is one solution.
But look, we could be lucky.
And which doesn't break down.
We could be lucky.
I believe that that's possible.
We could be lucky and just find one which breaks down.
Sorry?
We could be lucky and just from the first experiment see that this thing does not work, that there is a breakdown.
No, because it's...
we say it's not possible because people have done experimentation.
There are lots of experiments and they show that everything is okay. So I imagine, that's why I mean, there are other reasons I believe that in fact there are solutions that break down.
Well,
and you have to prove generic results. So I think one of the sort of the big uninvestigated area in PDEs is to come up with results which are generic. And that's very, very hard. I mean, that's done in dynamical systems, but it's done in dynamical systems because you have a measure on the space of solutions, and these kind of things don't exist in PDEs at all. So, this is kind of one of the sort of big open direction, so to speak. And of course, Jean has tried all sorts of things in that direction. You didn't talk about it, but I think those are very interesting. But they showed, there are examples that show that you can construct measures, but unfortunately, these measures are extremely singular in most cases, so you can't do anything with them.
They are not classical.
Right. But yeah, so I understand. So you want to make sure that there exists at least one for large data, and I believe that such a thing is possible.
But it's certainly there is this problem, but I have several other problems like that, assuming that you have a numerical analyst which has also some mathematical culture. I mean, you certainly would be able to give him a very good employment. That's my... because this is an area which is absolutely, at this stage, it's absolutely impossible to say anything whatsoever. It looks like the...
But it would be nice. I mean, numerically, it would be nice to actually look for things that do break down.
Yeah, but you can't find them if they are not there, so you have to start somewhere.
Or if they are unstable. I mean, the main problem is that they're unstable. I mean, this is one of the worst case scenario, for example, that I have for Euler equation is that well, the Euler equation is by definition, it's connected with Navier-Stokes equation. It's by definition the most unstable equation that exists that we have. It's the most unstable thing. Everything is unstable. Any kind of ansatz you make is unstable. So the worst things that can happen is that you have a dense set of solutions that break down. Each one is unstable. And the same thing happens with the solutions which, and there are also lots of solutions that exist globally and they are also unstable. And these kind of things, unfortunately, are completely out of touch. As far as numerics is concerned, numerical analysis will never detect anything like this.
But this, I mean, all the evidence is that this is much nicer than the Euler equation.
Yeah.
No, with Navier-Stokes, you can...
So you'll get large solutions. So in other words, there are global solutions which are stable. What you'll prove, in fact, I think that's what's interesting, that there are large solutions which are unstable.
Yeah, that's a byproduct of the argument. Yeah.
Because this proof gives also stability.
Yeah, of course.
If it works,
right. So you have regions, you have large regions.
The question is whether you can cover everything.
Yeah, that's a different
question.
Right. But you can give it stable.
Right. So you could you certainly have a lot of regions of stability. That's exactly what does not happen in scattering. So you don't have the scattering at all. You cannot expect any kind of scattering, of course.
No, here you will have scattering because
No, I
of
don't think was your equation.
yeah, I don't know. Yeah, probably not. Well, I guess.
But I will perhaps put question which I ready to face.
Money on the table.
Huh? But what?
Money on the table.
Money on the table. I said picture I put on the table. It's much more than money. No, every time I paid picture, picture went up in the same speed as solution of problem. So it was good payment. You may ask people who were paid. Okay, but and this is not necessary, just okay, first I will just say remark on concentration phenomenon, because it is a pity if some kind of reason why it is really work would be not clearly. And reason is, I don't need to put this on slide, I just may say, you see, anyway, no, but people who does not know it sound better when it is said. So this was some kind of formulas of concentration. Yes, you see this exponent inside. And then what I want only to say, and then it is more quickly to read, that in fact, you see, why concentration help in all results I said? Because concentration balance exponentially high entropy of n dimension. The only intuition we had before this theory appeared was exponential explosion of entropy. And it was nothing which balances in our mind. And what's happened is that exactly balance which give to us decay, which lead this concentration, yes, lead to regularity in high dimension and keep diversity under control. It is absolute surprise of computation that exact balance of rate of decay coming from concentration and expansion coming from entropy. It is more or less the same exponent. And it is constant, which you should put correctly inside, which balance them and bring result. It's of course only schema, but when you understand this, you started to believe in a lot of results which a priori you don't know from what place could come. So this is the idea how this thing work, okay? This is first remark, which is perhaps important to have in mind why all this result happened. A second remark is that just because of such incredible use which we have, I think it is the right way to think for generalization. And there exists two ways to generalize, to consider metric space without measure, and this is very important in situation of infinite dimensional spaces where no reasonable measure exists. And there exists way to extend, I will not talk today about this. We with Misha Gromov once defined what it is, concentration without any measure, but unfortunately, or fortunately, Pistov connected this with some inability of acting group. And in a sense, it returns us to some kind of substitution for measure. Weak, but anyway. But second is to use just only probability space. And besides the fact that we just have list of results, I will bring one, and here will be problem, only one, when in fact concentration does not come from metric. Besides this, I also have in mind non-commutative geometry when you have no distances, but such kind of very geometric notion as concentration may be seen in only measure space. And it's in fact under some kind of progresses. There is this attempt to do this. So I will not talk about this and only return to describe what is how to do only with measure. So one word which I did not write here is the following, just one word on the blackboard. So you have your space X, and you have function, and this function, say Lipschitz one function, and then take value, we call this Levi-mean, but it's median, which divide measure on two half part. Then if you take epsilon extension of this, epsilon extension, it is clearly that this measure will be measure of around one value, will be more above 1 minus 2 times that parameter which I wrote alpha x epsilon. And if alpha is exponentially small, then it means that this high probability function has exactly this value, one value. Because of this, if you consider integral, say, of positive function, integral of such positive function, it more or less equals this value. And if you have p power of such integral, then it will be more or less f to power p, which is exactly equal just, because it's just value of function Lf to power p. What we see is that L1 norm and Lp norm are equivalent. What? If p is fixed, constant depend on p, of course. So this is what I wrote here. This is what I wrote here, that it is practically equivalent. But because of this equivalence, we also understand, of course, that one side of such inequality is just Hölder inequality, we have probability measure. Another side, with no trivial, give you constant. So then it is clearly that if I would not know reason which I explained for this, and just would observe such property, then it is clearly, it's always connected with concentration. Function which extremely would not have this property. So higher p, smaller Cp, concentration is more strong. But of course it's also connected with class of function, and it is a point. It's not necessary, if you would have metric, it was not necessary only Lipschitz function for which is true. It may be smaller class, and then it's define completely different property. And this what happened in example. Just we first have example which we artificially prove, and then now it became clearly that we're just doing Cronk work. So P, C of P, and class of function for which this is define some concentration property. And I will bring example. In example, I will talk, I will give one example, but a little bit I develop this, a little bit just. I will take subset of Rn, which is finite set, and mu is, of course, counting probability measure. All class of function will be linear functions. It is linear function. It's only what I want to see. Okay, so this is what we will see now, how this works. Okay, so an example I start with absolute classic, is Hinchen inequality. You know, Hinchen inequality is absolute classic in analysis, and it says the following. You take point of vertices of cube, and I will just put in language I want. You take linear functional, which is the sum, and then Lp norm of this function is equivalent to L1 norm, with this constant root of p, or which is equivalent to L2 norm, which is just some square, root of sum of square. So for one side, for any p, this constant is c root of p. People of analysis know how important this type of estimate. It means that tail behavior of sub-exponential. A lot of things following from this. It is the best possible behavior. So this point, vertices of cube, is what I call Psi2 distribution. Psi2, it is root of p. I will not explain why. No matter. This is the terminology. So we have this set which is extremely good concentration, and it does not follow in from metric we may induce on cube or whatever concentration of cube we know. This is different type of result. But this is an obvious set. And now I will create from this not obvious sets. And this is what is interesting, that there is this extremely not obvious sets on which we have this type of concentration. And this is type of result I wanted to show. There exists constant C, such that there exists linear number, only linear, not exponential, of sign vectors, of which L1 and L2 norm are equivalent. So there is this very small set of sign, which I call well-distributed, on which there exists first traces of concentration, L1 and L2 norm, so Hinchen inequality in one form. Money, which I'm ready to put, not money, picture, but it is more, is to find this set. It is random set. How to find this set? In fact, we don't know to prove, and in another example which I know to prove this, I will not show, I believe that C may be any number more than 1, not exist some 100. Any number more than 1 already creates a situation, but constant would be depend on how C close to 1. This we don't know to prove even in random.
Because you put that average on the table. You have to give definition what will show the set, because the condition is recursive. So I give a primitive recursive function doing that.
What, just a moment. What you said?
Primitive recursive function giving you your set.
Giving what you say primitive recursive? For what?
Let me show. I'll show you algorithm how to generate this set.
Then what? You know, I think a minute. Just it is not clear that such set exists at all. This is non-triviality.
Once you know it exists, you will find the primitive recursive function.
Misha, I put any bet now that you will not prove the theorem for today evening. So just think what you say. What?
Misha is only saying that if theorem is known to be true,
yes,
then you can automatically write an algorithm providing a choice.
What e to power n? What you should go through all set, but I want to present this set, explicit present. Ask Avi what I mean. He understands what I want to say when I say to present this set. Whatever, to present, no. I don't mean computational problem here. Just a moment. As expanders, we had probabilistic and then we could present this. I believe I want this not for any computer type problem. I don't care on them. Just a moment. I believe, Misha. Your solution was so small picture that I may give you now because I may put this by myself. But what? But I don't talk about in this language at all. You don't understand. You know, this conference perhaps went too much in algorithmic. Do you understand that expander is good because it put...
The problem is that you have to define what explicit means.
Oh, I don't define this. Agree. It is behind the table. I don't talk about this. No. Okay. I did not decide. It is true.
So you also give one...
No. Point is explicit. I want to see this set, to understand this, not to have algorithm. I don't care. For example, I believe in the following type kind of solution, that if you have some discrete group which has extremely high, smallest, irreducible representation of high dimension, then number of points in this group will be n for me. And then this irreducible smallest representation, which is high enough to create proportion, this square, may give me this function. I want to see connection with some algebra behind, as it happened, for example, as expander. It's serious mathematical question. What structure stay behind? You see, we know that for extremely trivial question, like expander probabilistically is absolute triviality to demonstrate. We will need to involve quite a lot of mathematics to demonstrate this. This is not trivial to prove even in probabilistic sense. So I expect that much more complicated but very interesting structural mathematics will come inside. And this is my question about, and not about algorithm, which I don't care. Okay, so, but I would like to finish with this because one remark already, only this example will finish, another slide, end of this example. So you see, but more of this, we again have phase transition here, because if I would like to develop and to have this Hinchman inequality for other p, with constant root of p, but constant even will not influence, it's come automatically. Then we need to have now random set of the number of points of the order n to power p star. So p star is 1 between 1 and 2, and p star is p over 2, phase transition at point 2, and it is impossible to do better. So for smaller point, you will not find constant depend on p, not on the root of p at all, or not depend on n, which may do the job. So again, some kind of interesting phase transition point, and this type of, all these sets are non-trivial, but for p equal 4, it may be constructed. Yeah, I know, just. But we talk about p equal 1. And the last, about the same set, just last remark, and it's all which I wanted to add. for this is that in the same question, in the previous, P should stop in some point, and it depends on large set. But if we take number of points e to power root of n, which is still much less than 1 e to power n, we already create this inequality, this concentration for all p. However, constant would be p. It is P1 estimate, not P2, and it's impossible to do better. This is the best what may exist. And if we want to have P2 estimate, we anyway may do much better than 2 to power n, but we already need exponential. But for any gamma more than 0, for any gamma positive, which is extremely small measure of point, you already created a P2 behavior, which is the same already Hinchman inequality in full power, but with constant of C2 norm is C over root of this gamma. So it's all what I wanted. I saw that these examples show some kind of, that exists new direction here, that we indeed don't need metric, that we may work only on the level of measure set and to create extremely non-trivial. A similar thing was in fact used and in computational geometry by Lovash when he put random point in convex body, and to prove that some estimate is correct was needed Jean Bourgain because it was not work, and we again have complete picture of this. Okay. I finished. This discussion was good thing. Person may be satisfied in the end. Yes?
To ask a question which maybe connects, yes, we talk question of the this concerns what is a good Taylor polynomial approximation for functions of 10 variables. It's, I would even drop it to 6. 6 is a good number, for example, 6 degrees of freedom.
But is it semi-algebraic or not?
No, the question is like this. In numerical algorithms, it would be very nice to use Taylor polynomials of reasonable degree, 2, 3. It can give a really very big advantage. But then for 10 variables, I believe that the structure of a polynomial of 10 variables of degree 3 is highly governed by concentration phenomena. This what Koifman said yesterday, because if you have a product of 10 small numbers, then it is negligible. And say Taylor polynomial probably represents the sum of functions of small numbers, say products of 2, 3 variables with high accuracy. So
what Kalton talk about Brudny-Kalton work of but it's quadratic, linear, and cubical polynomial.
Yeah.
It's something.
Best approximations by linear and quadratic
Yeah. But it is more or less what Yoshi want. It was started point, but it's in another spirit, done by very recently by Kalton and Brudny. So you Brudny from Haifa, so you may find and ask. But it was something done which was we heard very recently. But I don't know what results are. They didn't go very far, but anyway, they have non-trivial results.
I think that actually understanding of polynomial degree 3 for 6 variables can give very big practical computational advantage.
Yeah, but you need to make some assumptions on the function somehow.
Oh yeah, I assume that, okay, I have in mind some very concrete examples. For example, you have these puzzles in motion planning where, okay, just you have to talk.
Take, I will take this up, don't worry, take. Come to this, and come to this, it will be up.
Okay. One of the problems, as far as I know, it is not a mathematical problem. You know, there are puzzles of the sort you have two rings, metal rings with small holes in them, somehow knotted in the space, and you have to unknot them. It's difficult even for a human being. To my best knowledge, in spite of the fact that all the motion planning algorithms are decidable and constructive or whatever you want, I don't think that there exists any computer program which can solve this simple puzzle in a reasonable time.
I don't understand. You have two rings and then what?
You know, with small holes in them. Then you have to unknot them.
I don't know. I met this practically, and for me it was very difficult. Now, as far as I know, for computers it's extremely difficult, practically impossible. Now, if you work with the standard methods of motion planning in robotics in phase space, you just have to compute the distance function between two objects. But it is a function of 6 variables because of 6 degrees of. If you fix one of the rings, then you have 6 degrees of freedom of the second ring. Now, this function is very complicated, but it is highly smooth. You can use as many derivatives as you want. But, okay, so this is... Yes, I have programs which work, say, up to 3, 4 variables, and they are already very complicated. But 6 seems to be very practically important, but very complicated stuff.
I don't think it's the right approach to this problem.
Actually, I don't want now to enter, but let me put the following. In degree 3, in dimension 3, using Taylor polynomials only of degree 1 can simplify the analysis in orders of magnitude. So Taylor polynomials do allow to exploit the smoothness of the problem. But the question is, what is a Taylor polynomial in dimension 6?
No, but point is, concentration phenomenon by idea cannot help in such problem because whatever you look for is extremely small feature of the thing. And any kind of high probability, perhaps it is not what I see is of help. But what paper I mentioned, they exactly deal with this approximation, and I completely forgot this now, what are details. But if this is of the spirit, but they did not move above approximation by quadratic polynomial, which is maybe also good sometimes.
Oh yeah, but actually we discussed several years ago this problem. So I believe that it may be an interesting theoretical problem, maybe a kind of non-linear concentration, just to go to polynomials of degree 3. Okay.